Overview of the presentation. We're going to talk about what Mars to Go is. It's a concept I came up with about 4 years ago and presented here at this conference. We'll talk about it. And we'll go over some of the advancements that we've had with propulsion, additional things we can talk about in regards to life support, existing spacecraft systems, what we might need to develop if something like this were to be carried out, and then we'll just quickly talk about an example architecture next. Back during the 1990s, when Dan Golden was the administrator of NASA, he had a mantra. It said, better, faster, cheaper. Most people since that time have kind of come to say, well, you can pick 2 of the 3. And the original Mars to Go concept was like that. It was faster, it was cheaper, but in terms of mission safety, in terms of margins, etc., it probably was not better. But sometimes better is the enemy of good enough. And like fast food, the whole point of the mission was simply to go. So it's kind of flags and footprints. Next. The idea was to keep things in space as light as we could, because at the time we didn't have an SLS or a Falcon Heavy or potentially a Raptor from SpaceX. The idea is still to minimize the amount of mass that needs to be placed on the surface of Mars. Entry, descent, and landing is a large bottleneck. We don't have the capabilities to land as much as we'd like. That will take technology developments, although some of that is being done over the past year. And obviously to, as we said, avoid advanced technology developments. Now what it's not, I'm not recommending this or any version of it as an actual way of saying, hey, let's go to Mars. Okay, this is just a thought experiment saying, if we had to go as soon as possible, how could we do it as quickly as we could? Thanks. So here's an overview of the original Mars to Go, like I said, we were going to do. It included 4 launches. The first launch was of a Delta IV Heavy, and it would send 2 Mars Science Laboratory-sized landers to Mars. These were to be ascent stages. They were sent up with a little bit of hydrogen, kind of like Mars Direct, but they had different fuels between the first and second stage. The hydrogen was contained in the first stage carbon monoxide tank, which was then used to make methane for the second stage, and then refilled with carbon monoxide from the Martian atmosphere as it was broken down. Next. Later, a Falcon 9 Heavy, not a Falcon Heavy, this is before the Falcon Heavy, so Falcon 9 Heavy, which had about half of the same lifting capacity, would use a Centaur stage and send 2 smaller, maybe 8-ton size propulsion stages towards Mars. Next. Another Delta IV Heavy would place a landing vehicle on a direct course for Mars to be placed into orbit by a propulsion module. Next. A Falcon 9 Heavy would then carry a single crew member inside of a SpaceX Dragon capsule. Next. Next. So as those Mars ascent vehicles we talked about would land on Mars, they would deploy their solar panels and begin producing propellant. Next. One of the propulsion modules would be placed into a low Mars orbit for later use. Next. And then the landing vehicle, SAVI stands for Surface and Ascent Vehicle, because it will be used on the surface of the rover and then will later be attached to the propulsion stages to ascend. Next. And then the crew finally arrives at Mars and breaks into orbit. Next. The 2 dock. Next. And then through a little, no, previous. And then through a hatch inside of the Mars aeroshell lander, which is used to place the radioisotope generator at the last minute, the crew member would crawl into the very cramped surface vehicle. Next. Then it would land with the crew member on board. Next. Next. And then just like the rovers, it would use a sky crane and it would set down this small landing vehicle. Next. It would deploy so that the person inside could finally sit up and go around and collect samples. Next. Then it would reconnect with the propulsion stages, which are also on top of rovers, and then ascend to orbit next, and next. It could only make it to low Earth orbit. It didn't have enough fuel to make it up to where the Dragon capsule was still waiting. So that propulsion module we placed there earlier would dock with it and then carry it up to the higher orbit next. Where it would then dock. You can see the size. I mean, it's a box in comparison. Where it would dock with the Dragon capsule, and then the crew member could return to it next. They would reattach to the other propulsion module left higher up, and then return to Earth next, and land. So that was the original Mars to Go concept. We used a bunch of small vehicles and existing or nearly existing rockets at the time. Next. We have a lot more now, so there's an updated concept. The biggest thing we have, you'll still see the Delta IV Heavy is there. It has heavier engines, so it can lift a bit more. But we have the Falcon Heavy, which can lift 53 tons to low Earth orbit or 14 tons to Mars. And we have a space launch system, which can put over 100 tons. Well, it's supposed to be able to put over 100 tons into low Earth orbit and launch 32 tons towards Mars. Next. These are the upper stages that go along with it. The exploration upper stage is the one that is still in the earliest phases of development. Next. And these are the propulsion requirements. They're taken from the NASA Interplanetary Mission Design Handbook. At the top, you can see what the delta V requirements are. According to this, Mars capture requirement is about 0.9 kilometers per second. Variations between 0.7 and 0.9, somewhere in that ballpark. Next. Trying to get back from Mars orbit, you're going to want at least 5.4 kilometers per second, minimum. I designed for closer to 6, as you can see here. A lot of the same numbers, 0.7 kilometers per second for the less stringent capture requirements. Next. And then this is from Inspiration Mars. They said, we want to send 2 people around Mars. We want to do it in about 500 days. And here are what we think the mass requirements are. We're not doing a 500-day trajectory. We're doing a full, almost 1,000-day long Mars mission using home and transfer orbits. So, next. We have to double those. That means that you're going to need 11 tons of consumables for 2 people, minimum. The volume required, and here's where you run into a problem with simply having a Dragon capsule, because it has 10 cubic meters of internal volume. You're going to need 48 cubic meters of material for the 2 people before packaging factor. So that could be as much as 72 cubic meters. There's nothing that big that's cheap and available. So after thinking about it, I decided I could split it up between 3 cargo vehicles. That was not in the abstract. I've added that since I found some better numbers. This also allows you to reduce the consumable amounts to about 3.7 tons for each vehicle, although the primary one can carry quite a bit more if necessary. So, by the time you add in the additional volume required for each crew member, your vehicle, a vessel configuration is going to require 42 cubic meters. So you have 9 cubic meters inside of an Orion capsule, for example, and then you need some module that has 33 cubic meters. We'll get to that. Next. So here's the Orion. It's being developed by NASA and DSA. It's supposed to have an endurance of about 21 days. It weighs about 21 tons. And it will be used as the mothership for the architecture we'll consider briefly. Next.
Excuse me, when you say endurance of 21 days, what do you mean?
The life support systems on board will support a crew for 21 days. So, yeah. There are some of the numbers. The capsule itself is about 9 tons. The service module is about 12 tons. There's about 8 tons of propellant on board. All by itself, with nothing attached, it has a delta V of 1.6 kilometers per second. Next. In order to capture the vehicles into Mars orbit, there are a lot of things you could do. You could theoretically aero capture. The variability in Mars's atmosphere, depending on temperature, solar flux, etc., makes that a tough proposition. You could use magneto shells, still not developed, but early testing. Great ideas, a lot of things you could do. None of them to the advanced state of simply using propulsion. So that's what I went with here. This is the Orion service module being developed by the European Space Administration. And then the Star 48 series motor from ATK happened to be sized correctly for the version of the exploration augmentation module we're about to see shortly. Next. This is a proposal by Orbital Sciences Corporation. Their Cygnus spacecraft currently has a pressurized cargo module that has 2 segments. They would like to extend that to 3 and will very shortly do so. And here they propose using 4 segments. If you look at the volume required, it turns out to be exactly what we're looking for, 33.5 cubic meters. And about the same payload mass. It's a self-contained spacecraft, so it can do its own maneuvers. Next. Its total mass, including the cargo module and the bus, is about 4.4 tons, estimated. Next. Radiation protection. By splitting it between 3 vehicles, I can actually fit everything in each vehicle. But it still takes up a lot, so the supplies provide some protection, and then the water would be stored in bags around it. You could use a water wall that's being developed by NASA. Wouldn't use it for things like treating the wastewater that's still too low on the TRL level. But you could use it for storing water. Doing this, each one could have 4.3 grams per square centimeter of protection. That's not a lot. If you carried all the water on one vehicle and then transferred it between as you used up each one, you get about 13 grams per square centimeter. Then throw in the supplies on each one, 19 grams per square centimeter, and it's pretty decent for protection. Next. The entry system. This is the Mars Science Lander Aeroshell. And more recently, in the past few months actually, there have been improvements to this design. They've started using a low-density supersonic decelerator, which is an inflatable device that can increase the surface area at low velocities so that you can have a bit more landed mass. Instead of maybe a total of 1.6 tons counting the lander stage, you can maybe get closer to 2.7 to 3 tons. Next. Also, SpaceX has started testing supersonic retropropulsion. And they had made a proposal to land one of their Dragon capsules on Mars sometime in the 2020 time frame. No funding, it's a proposal. Using that technology. They think they can land approximately 2 tons inside of the capsule. Next. There's some of the statistics. Overall, basically it would weigh 10.5 tons at the start of the entry. Next. The one thing that needs to be developed that I can't find an equivalent for is a Mars ascent rocket stage and crew capsule. And because the volume and the mass are so limited, it makes for some interesting arrangements. You can see the exterior of the aeroshell there, and here's what something on the interior would look like. The blue tanks are oxygen tanks. The red tanks are methane tanks. The green stub at the bottom is an aero plug for propulsion. There's a propellant production device on top, stowed solar panels, etc. Next. So I treated this kind of like a one-stage vehicle with drop tanks, akin to a 2-stage vehicle, but not quite. The first stage would use 2 tanks of each type of propellant, and with a mixture ratio of 2.63 oxidized with fuel, I should say ratio, not ration, you could have a specific impulse of 340 seconds. The second stage, however, to keep things balanced, actually has a fuel ratio, oxidized with fuel ratio of 5.25. That gives you better specific impulse. It's still not the optimal 360 to 380 that a ratio of 4 would give you. The plug has a thrust of about 15,000 pounds. That's about the total thrust, or the total mass of the vehicle at takeoff. Next. So for the ascent vehicle, there's a crew enclosure. It's not even a crew vehicle. It's an inflatable bag, basically, that a crew member can sit inside of to have some protection while ascending. There's some support systems for it, including some oxygen tanks and some CO2 scrubbers. But basically the crew member will be inside of a spacesuit most of the time during the ascent. There are some mass units right there. At landing, it would weigh about 2.8 tons. Next. The power production system for this would use ultraflex technology. It's been used on Mars before. It has an efficiency of about 30% and a specific power of 200 watts per kilogram. The idea here is to have about 4.25 kilowatts peak power production. Next, with a total panel mass of 48 kilograms. Now, I don't have numbers for the power requirements for electrolyzing carbon dioxide, but I do have numbers for the Sabatier reverse water gas shift reactors. So that's about 5 kilowatt hours per kilogram required. If we have 1 kilowatt average power, or 4.25 peak, about 1 kilowatt average, it would take 2.5 years to produce all the required oxygen. That's why it goes out in advance of the manned system. Next. So for an updated architecture, using some of the systems we talked about, we can start with a couple of Delta IV Heavies, and they would lift some of those ascent vehicles directly to Mars, where they would land, and then start producing propellant. Next couple. Next. And then sit back. And then a couple of years later, same launch window, you could also launch a Dragon capsule that would be used for landing, along with a couple of Orion service modules that would be used for propulsive maneuvers that are attached to it on this Space Launch System launch vehicle. Next. During the same window, second set, we could launch some Falcon Heavies. They would send those exploration augmentation modules, and then those would be attached to the star motors, and those could break into Mars orbit. Next. Same thing. Next. Finally, once everything is assumed to be nearly on its way, the crew would ascend on top of the Space Launch System as well, and they would have one of the augmentation modules going along with them. Next. So, pretty much as we described before, the ascent vehicles enter the atmosphere, they produce fuel. The Red Dragon goes into Mars orbit. The crewed Orion spacecraft, after launching, separates from its upper stage, turns around, docks with the exploration augmentation module so that you have a full spacecraft that they can use during the duration of the outbound journey. And at the same time, they have 2 other EAMs with them that they can use in case of an emergency. And then everything enters orbit around Mars next. The crew separates from their exploration module. They dock with the Red Dragon. They land on Mars. Because at apoapsis, they're in a highly elliptical orbit around Mars. So at apoapsis, they can make a really small burn, like 20 to 25 meters per second. And that will allow them to perform the re-entry operation. They land on Mars. After a short surface stay, I forgot to talk about that. There are enough supplies on board for 25 days, but the planned duration is only about half of that. Next, they can go around. They'll have some small wheeled rovers, kind of like a lunar rover. It won't be a big truck. It won't be pressurized. There's not enough massive volume for that. But they can use that to do their sorties, as well as to transfer themselves over to their ascent vehicles. They will then ascend and rendezvous with their Orion spacecraft. The Orion spacecraft will redock with another exploration module. And then they will dock with the service module from the Orion, perform the TEI burn, and return to Earth. And that's the idea, using the technologies almost in hand. Any questions? Yeah.
So the outbound and the coming back, is that with artificial gravity or?
Mm-hmm.
So those would be microgravity trucks.
The Medical technology is improving in space. There are things that they can do. They can give you an osteoporosis shot, for example, that's been shown to actually increase bone density over a 6-month period. Russians have shown that exercising can keep muscle mass up. There are things you can do. Like I said, I'm not advocating this as the way to do it. Just saying that if we had to do it, there are ways we could do it, and there are workarounds. Yes?
How long would you stay on surface?
Less than 2 weeks.
That seems awfully expensive to get there for 2 weeks of activity.
That's why it's called Mars to Go, purposes to go.
Okay, so this would be the initial ones, and then what would be the actual follow ones from there?
You'd probably come up with a more sustainable architecture, hopefully. That's what I mean, you'd want to use reusable rockets. You would want to possibly use cycler. You'd want to have more advanced technology that doesn't require as much propellant to get up and down. It's a thought experiment. What if we had to do this in a half a decade? Thank you.